Okay, I update the schedule a little bit on the website. Please take a look at it. If you are not seeing these updates, just refresh the browser. I'll be able to see them. So today there will be a new tutorial to be covered, new contents, and the tasks within that tutorial will be due next Thursday, right before the class. And next Tuesday there will be a quiz 2 on floating point representation. It's going to be on paper. I'll give you a quiz on the paper and you turn it in class, right? So be here on time next week. And after that, on Thursday next week, we'll have a quiz 3 for the parity bit generator and checker, which is being covered today. And homework 4 as well will be available. So this afternoon there will be a lab, and pretty important stuff will be covered in the lab. It's a 2-week lab. I mean, if I have time in the lecture today, I'm going to cover the materials in the lab, so you can directly come over to the lab and start working on it right away. If not, I probably have to use like 15 to 20 minutes this afternoon to cover this stuff in there, right? So pretty basic stuff at the very beginning of this new tutorial. So, but before we get into it, I want to, let's review the logic for the half adder. I know it's pretty simple, but let's take a look at it to make sure everybody is on the same page.
Logic for the half adder.
Yeah. Great. So in C++, you can directly just put x plus, for example, y equals x plus y. That's C++, right? But in Verilog, you are not allowed to do that. You are programming a circuit instead of a calculation or operation in there. Okay, even though it looks very similar to C++, but it's not C++. So if you have x, y, and s 0, 0, 0, 1, 1, 0, 1, 1, right? So you're getting 0, 1, 1, 0. Okay, and you can immediately tell s equals what? No, yeah, so you look at these two. So when they are different, you're getting a 1. When they are the same, you're getting a 0. So you can directly tell, right? It's extra logic in Verilog. Okay, so for CL, this one doesn't have a carry out, so it's 0, no carry out, no carry out, and carry out. Okay, so CL equals what? Yeah. Okay. So what's the problem if you directly just put a s equals x plus y in there? Since you are allowed to do addition in Verilog, we have been adding ones to a bit, right? So what's the problem? You don't got to carry out. Yes, but what else? But when you compile this thing, it's going to report error. You have to think about hardware all the time, right? So if I just have a variable look like this, it's usually just how many bits in there. If I just read s over here, it's just 1 bit. I'm assuming a 1 bit. So for this s, how many bits are in this s? Yeah, it's just 1 bit. So there's no way that you add 2 bits into 1 bit. So hardware-wise, it's not going to work. It's going to report error. But even C++, you can definitely do it. It's a software. But here's a hardware description language, so you cannot do that. You just have to always think about the digital circuit instead of programming when you are doing Verilog.
Can't you add 2 binary numbers together?
Yes, but you have to make this one wider.
Okay.
Right? If you have an s, declare it as a 1 to 0, right? So it's a 2-bit s, then you can, do addition, no problem. But it's just a 1 bit, then you cannot do it. But it also doesn't make sense you have a 2-bit ASC for adder, right? It's just a 1-bit thing here. You know what I mean? Yeah, but you can combine S and CL as one number, which also works. So that's the half adder. For full adder, I'm not going through the logic because I have done this a lot in 241. You can look at the derivations in the logic class. But S equals, if you have 3 inputs, A, B, C, I, and 2 outputs, right? That's a full adder. So S equals what? A XOR B XOR CI, right? Syntax-wise, can I write this in here? Is there any error with this?
I feel like you need a parenthesis.
Like this? Yeah, either way, there's no problem. Okay. So for CL, there are 2 forms. If you're looking at some of the examples online or in some of the textbooks, both are, either one is correct. So it is AB or A or B CI. But can I write this way? So this is C++, right? This is a logic expression. It has to be converted into Verilog. If you convert this one to Verilog, it becomes what? A and B, right? Okay, or A or B and the CI. It's going to run the AND logic first and then the OR logic. So it's okay to not having a parenthesis here or here. You also see a format. It's like A and B or A XOR B and the CI. Let me double check. This is correct. Yeah, that's right. So you can either have XOR or OR in there. It's not going to give a different result for the full adder. It's because when you group, you have AB, CI. Could you tell the CL over here really quick? If A, B, C, I, 3 numbers added together in the truth table, are able to tell the CL?
Just add them?
Yeah.
Yeah.
Zero plus 0 is what? For CL is 0, right? 0 plus 1 is what? Wait, for CL, carry out.
Oh, 0.
Yeah.
I see.
Are we getting that? Is that clear? There, Noah? Yeah, good. 0 plus 1 is 0, right? 0 plus 1 plus 0 is 0. 0 plus 1 plus 1. So 1 plus 1, you got to carry out, right? 1 plus 1 plus 0. 1. 1 plus 1 plus 1. It's going to be 1. So 1, 1, 1. Adding together, it's a 1, 1, right? 1 plus 0 plus 0, 0, right? 1 plus 0 plus 1, 1. Okay, there are a few ways, different ways to group them. You can do this, right? And this,
So you're adding a 1-bit number to a 2-bit number?
No, they are all 1 bit. If you look at the input of the full adder, how much you have forgotten from logic, that's I'm not really sure. I don't want to make it too boring when I'm going through the basics. Is it too boring or it's okay? It's okay. All right. Okay. So full adder, you got 3 bits, right? For half adder, XY, you don't have a C in. That's a difference. So for half adder, it's not adding a carry in. It's just a 1 bit plus 1 bit. You get an S, which is the summation, the sum, and a carry out. For full adder, you are considering the carry in as well. So 3 binary bits being added together, and you are getting a sum and a carry out. Okay. So one question here: is this a 1-bit full adder or a 3-bit full adder?
1 bit.
1 bit full adder, right? Okay. So when you are grouping these numbers in the truth table, you can either group this one, single out this one, and group these two and these two to simplify it. But there will be it's called static hazard, static one hazard. If you don't group this single one with any of the other ones, or actually this one, it also works logic-wise. So if you just do this, group this one and these two and these two, you are eventually getting this logic expression. But if you group this one with this one here, so it's just all the twos, this pair, and this pair, eventually you are getting this. So logic-wise, there's no difference. But this is definitely better. So we have been using this one for a lot of the IPGA examples, and also in the future you are taking digital VLSI circuits. We're also using this expression instead of this. So this is definitely preferred. Okay.
So functionally, CI isn't really any different than A and B. It's just that's the terminology that you use.
Yeah, it's just the 1 more bit. So carry in from, if you have multiple stages, then this carry in will be a different, will be another stage being feed. It's going to feed in that CL into C in if you have multiple stages. We'll have a lab. I think that's going to be lab 4, lab 5. Just working on multiple bits of full adders and being implemented onto IPGA. Okay, but this time we just need to know that this is logic expression for the carry out. Okay, so you can directly code it up in your Verilog and implement it on the IPGA board. So after that, in the tutorial, it covers decoder. I don't know how you guys do it, but when I was in college, if I learned all these basics in one semester, the next semester I'm going to forget everything after the final exam. Just right after the final exam, I just going to forget everything. So my brain will automatically erase all the materials in my brain. They'll be gone. But it's been a few years for guys, so it's good to review them, because very likely if you are reviewing for a digital design or digital verification job in the future, it's very likely they are going to ask you this during the interview. We'll directly put it on the paper exam for the interview. Like interviewing with NVIDIA for the digital design job, and you are going to expect some of the digital logic problems on it, and Verilog as well. So for decoder, XY, you got 4 outputs: Y0, Y1, Y2, Y3, 0, 0, 0, 1, 1, 0, 1, 1. It doesn't have to be exactly the pattern as a classic decoder you have seen, right? So the classic decoder output pattern is usually 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 1, 0, 0, 0, 0, 1, like that. Just shifting that single 1 to the right. And then you design the digital circuit accordingly. You just look at each output each time. Okay, and make sure you guys know how to do it. Let's just run for Y0. So if I'm trying to design the circuit for Y0, and what is the logic expression is over here? So Y0 equals what?
NAND.
Hmm? What?
NAND gates.
NAND gates? It's not NAND gates, very close, but it's not really NAND. NOR. So NAND is X, Y not, right? NOR is X, Y, X or Y not. Right? But this is X not or Y not. You gotta be clear that this is different. They're giving you a different result, right? So know how to do it. Great. Same for Y1, Y2, Y3. So you can definitely find out the logic expression for each output. Okay. So if you have a different pattern here, for example, I'm flipping this bit to 1. Is this a decoder as well or no? It's also a decoder, just a different pattern of outputs. It's fine. I can also design a digital circuit for each output. It's going to work. Definitely, no problem. Okay.
Why does NOR not work for the first one?
No. So this equals.
It's the output of OR inverted, right?
Oh yeah, that's right. You were right about first place. Sorry.
I was confused.
Yeah, that's right. Yeah, De Morgan's law. That's right. That's right. Yeah. I was thinking you guys are trying to equivalent this to this. Yeah, that's right. Okay. Okay. All right. So that's a decoder and encoder. Is a different circuit. So it's just the opposite of the decoder. You have more inputs, more bits of inputs than the outputs. So if, for example, D3, D2, D1, D0, and Q1, Q0. 0, 0, 0, 1. So follow the same classic pattern over here. 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, see the 1 is diagonally distributed over here. So the outputs are 0, 0, 0, 1, 1, 0, 1, 1. So if you have multiple sensors in a certain circuit, okay. So if one of the sensors is on, it's trying to output a code, a certain code. So it's encoding it, right? So you get a 1 being turned on, so it's encoding, it's sending a code to the system. So what is the potential issue of this one? You have more inputs than the number of outputs over here. What's the potential problem? Can you think of? Multiple inputs on the same time, then what? You do have a corresponding output, but it's going to be the same because you only have 2 bits for the output, right? There are only totally 4 different possibilities for the output, right? If you have a different bit is on, then you can get the same pattern here, right? Because if you have 4 inputs, 4 bits for the inputs, how many possibilities are in here? 16, right? But only how many of them are being listed or being used, being considered? Probably being considered. Only 4 are being considered. So you have 12 left, right? You have 12 cases left, but you didn't consider it. So what if you have a input like 0, 1, 1, 0? What's going to happen? So let's write down the digital. So not considering this output, this input here for now, okay? For Q1, what is Q1? D3 not, right? D2, you have to look at this line because of this one here, and also this one for this line, right? So it becomes D3 not, D2, D1 not, and D0 not. Right? Or this guy. D3, D2 not, D1 not, and D0 not. Based on what you have in the truth table. Okay?
Can that just be simplified to D3 or D2?
Yeah, definitely you can simplify it. Oh, it's not. It's so if you take this out, right? It becomes D. I don't think so. It's D3 XOR D2 and D1 not, D0 not. Right?
That's confusing because D1 and D0 don't have any effect on it, do they? Like you can get an accurate logic.
They gotta be 0 to make it happen.
Okay.
Right? Because that's all the bits defines that result. So they must be 0 here.
Okay, so you have to include all the bits.
I have to encode all the bits, right? Yeah. But the problem is you don't have all the possibilities listed over here. So I have to consider these two. So I have to include all the things over here, which will cause a problem. For example, if I have one input, so the sensors are designed not to be on at the same time, for the multiple ones to be on the same time. But there might be some issues like noises or disturbance of the system and getting one of the bits getting flipped, right? So if these two bits are getting flipped at the same time, so you're getting D2 and D1 are on at the same time, what's going to happen to it? If you plug in all the numbers over here. Let's try it. So if D1 and the D2 are both ones and the other two are zeros.
There's two different outputs for Q1.
This is the one.
There's gonna be two different outputs for Q1.
Two different what?
So, okay, whatever. Let's just go through that.
Yeah, let's plug in these numbers here first, okay?
You flip it to 0, right? Because one of the inverted D1 and D0 goes to.
Yeah, so this one,
0.
it must be 0 for the entire thing, right? So it's going to be 0. What about Q0? We don't have Q0 here. I have to write down the Q0s. So if this is 0, so it's going to be off. Yeah, let's write down Q0. What is 0 going to be? Q0. D3.
D2, D1, D0 not.
Right, for Q0. And then the last one, which is
That's right.
then so it'll be definitely D3 XOR D1, right? Let's make it cleaner here on the next page. So D2 and D0 So this becomes 0 as well. I don't know what is wrong over here going on with the logic. Let's skip this for now. It's just taking more time than I expected. So the problem was if you have a lot of cases were not being listed in the truth table. Let me show you that one here, right? So I got four inputs, but you're supposed to have 16 inputs possibilities listed over here, but because you have like 12 or 11 over here in this case, it's not being listed. So if 2 bits are getting flipped at the same time, you are possibly having the same result being shown up over here as the output. Because your logic expression doesn't cover the rest, so it's getting the same result. So the way to get rid of that problem is to list all the possibilities. Okay, it's called priority encoders. So how do you list all the possibilities? Have you learned the don't cares in the truth table? So don't cares is just to place the little cross over here. So it actually covers both cases. So don't care is when you are writing down that logic expression, you just don't care about it. So whenever one of the bits is getting flipped, so for example, for this case, whenever this one is being flipped, then you definitely are outputting this certain result. Same for the second row. If this one is getting flipped, and you don't really care about this one, so just don't cover, you don't write that D0 into logic expression. So and then that one equals your expected results. So in that case, you don't have to list all the possibilities, just to have a don't care over here. It actually covers all the cases. So in that case, whenever a 1 is being flipped, it's going to trigger that output. Doesn't matter, like for example, you have a 1 here and you got another 1 over here being turned on. Okay, it won't, because whenever this one is on, right, if you look at D1, this one is on, it's going to show up this 001 result. All right, but because that you have a don't care, it could be 1, could be 0, it doesn't matter, right? It covers all the cases. So it only care about this one here. So whenever this is 1, it doesn't matter what about these ones are. It's going to directly output 011.
So your logic expression would only include everything to the left of the axis?
Yes.
Okay.
Yeah. So in that case, so all these bits won't affect the results. Okay. So we can list, write down the logic expressions, something like this. You can see this is an 8-bit input encoder. You can tell that I'm not including all the inputs, right? It's different lengths. So only the first one covers all of them up to D1. Am I missing anything? So it's number 1. Okay, so this one, right? So covers until D1 because D0 is don't care, so I didn't include it over here. Okay, so in that case, whenever this one is being detected, it will output that exactly result because it's just whatever being described on the truth table. Okay. This is called lookup table. Lookup table. It's using a case statement. Okay, always at. Remember what X is over here? So X is called the sensitivity list. So whenever X changes, it's going to update all the things in the always statement. Okay. So when X equals, so just look at all the writings here, all the code here. Which one represents X? The value of X in the case statement. So when X equals what? Where is X?
Is each letter X one bit in the X vector.
So X is 8 bits, right?
Yeah.
Yeah. And in Verilog, you're allowed to put an X there, which means don't care.
X is always not.
Yeah, don't care is allowed to put an X over there, but for this X is different from this X. So this X is don't care, I mean this X is an 8-bit binary number, right? So where's X? Where's this X? It's checking where? Or what are the options for this X? It's just here, right? So these are the numbers. If you check this X, if it equals to which entry, it's gonna execute the following statement over here, okay?
So all it would need to match with that first one is just having a 1 and the most significant bit.
No, you can see it sometimes it's being shifted. So that's all the possibility in the encoder's input. It could be zeros in front of it, and then you got a 1 here, right?
Mm-hmm.
So 1 is not necessarily to be an MSB. So this case is an MSB, but the second one, all the following ones are not, right? So X is a number, okay?
Yeah.
It's an 8-bit number. And when X is, for example, this number is an 8-bit binary number, which is 1 and don't cares, right?
Right. So that's what I'm saying. It would select that one if the 8-bit X number had a 1 in the front.
Yeah,
it doesn't matter what the rest of it is.
Exactly, for the first one,
yeah,
yes. Yeah. So if X equals this, right, it's going to select the second one and put a, so what is this number here? It's just whatever in the truth table. So this is just 110, right? If you have 0, 1, let's go back to the encoder's truth table, see if that works. So that one is this, right? 0, 1 and OX. So you're outputting a 110 here for the encoder. That makes sense? Yeah, easy.
It's like a switch statement.
It's a switch statement. Yep, that's right. I don't think they need to put an X over here. It should be just a case. I think that's just typo in the textbook.
Okay.
I don't think you need
the parameter of case the letter that you use to fill in the don't care spots. Like, why is it case X?
I don't think they need an X. It's just a case. It should be case and parentheses X.
In parentheses, why is it X? Is that because you're passing the?
You are passing this one,
Okay.
right? And also, that's a good question actually. So you are passing X to the one of the entries over here. Okay. So what is this doing though?
Yeah,
What you got think? What is this
I
doing?
don't know.
What you think, Noah? What you think? Why do you need X over here right after?
So as long as X has an input, right? As long as there's something for that.
Very close, yeah.
Anytime X changes.
What's the name of that little thing in the argument in the parentheses after always? What is the name of it? No, I mean, what's the name of the argument in here? Remember? What did we call it? It's a sensitivity list. Sensitivity list. So whenever that one got changed, so always, again, it's a hardware description language, right? Whenever that one got updated, the switch statement will be executed. Otherwise, it's not. It's not a C language, right? Or C++. It's always being executed from top to bottom and like cycle back and forth. It won't run it at all. It won't update it unless S get updated. So always add something sensitive being changed. Then it's going to update all the values in the storage. So these are like D flip-flops when you trigger it. Or this could be an enable pin of the AND gate, right? So when you enable it, it triggers all the it's like a parallel in, parallel out of the D flip-flops. It's going to trigger the updates. It's updating all the values over here. So positional encoders, in my practical robot design class, we did use a encoder to accurately control the robot, the motor's rotation. This is also called an encoder. It's a hardware equipment, a little component in the drawer. So it switches to a different location. It's giving a different input code for a certain output. It's a mechanical part. And we don't have any tasks associated with this mechanical part for this class. Multiplexers, I'm not sure if you guys still remember multiplexers. You got a two, if you have a four inputs to be selected, how many bits do you need for the selection bit? If I got four inputs, how many selection bits do you need? Two. What about eight? Eight inputs, how many selection bits do you need?
4.
8. So eight different options, right? Therefore, how many binary bits can give you 8 different possibilities or different options? 3, right? So it's going to be 3 bits, 2 to the third power. So 3 bits can give you up to from 0 to 7. So it's 8 different options. You can switch in between the 8 different inputs. So we're all 16. 4, 17. Yeah, that's right. And then you can code it up in Verilog. You know, building all these digital blocks just becomes so simple. I don't know if you guys really appreciate that new technology. You can directly code it up and implement it into FPGAs.
So wouldn't you want to use like behavior modeling versus the like, data flow utility?
For this example?
In general.
In general?
So I'm like playing around with the comparator.
Yeah, for sequential circuit, you just have to use the behavioral. But for computational logic, I think use data flow is easier because just the one logic expression is very similar to like just writing in C++. Yeah. For example, this one, if you can design or draw the logic gates on the paper, you can definitely write down or type the data flow Verilog code easily. It's just a few lines of code. So this is structural and this is data flow. You can tell, you know, you probably prefer the second one, right? And you can use a case version, will make it even longer. It makes sense. The multiplexer is when you have what you want to select which, right? So if you use a switch, or it doesn't have a switch here, but it's a case or switch statement. You can switch in between all different options and send it to the output. So why do we have S or X here? So this is an 8-to-1 multiplexer. 8-to-1 multiplexer. How many bits do we need for the selection bit? For the selection bits, 3 bits, right? So that's why S, you declare S as 2 to 0. So I have 3 bits in there, and X is the input. So that's the 8 inputs. So you need a 7 to 0. Okay. And Y is a register type because they are assigning a number to it. And should be a default value, but it doesn't. You can also assign a number to wire. I think for this case, it doesn't matter. I don't think it matters. You don't have an initial value. It can be wire or can be register type. So if we look at the sensitivity list, right? S or X. So or is definitely a keyword here. And why do we need an S or X? Why do we need an X? Yeah, if the input changes, right? If the input changes, the certain value at a certain bit need to be updated to the output if that one is selected, right? So definitely the input changes, we need to update it. So if the output, if the selection changes, which means we want to select a different input, we'll send it to the output. So we do need an S or X to be, whenever they're updated, you want to update the output because that's how that works.
So this is saying that when S or X changes, then S will be assigned these values?
Yeah.
Okay.
Mm-hmm.
And then, okay. So like,
So when S or X change at all, any of the bits change, then S is going to change, but X stays the same.
Yeah, S is not if only. I think it's just the S or X change, right?
Yeah.
It's gonna get into the statement and update Y. It's gonna update the output.
It updates Y, it doesn't update S.
Yeah.
Okay.
No. Only as changes, it's already changes, then it's being detected. It's going to come over here. Y is not changing, so it's just a case of Y's, right? So Y could be one of these. So if it's S is being detected, then it's coming into here and getting to one of the entries and update Y, right?
Could you do like a OR operator, like the line, instead of writing OR?
Or operate? I don't think so.
Okay.
No,
it's logical.
it's a logical.
It
Yeah,
was.
it's not an operation there. Mm-hmm.
So is it still fabricating that on the board if you use the OR?
Mhm. It could be an OR gate. I mean, it's more complicated than that. I mean, it also depends on different companies who fabricate the FPGA. It must have different structures in there. Yeah, we don't have to care about the details of the, unless you're a process engineer in one of the companies. Parity generator. So the parity bit is being used for check errors. It could be an even parity generator or an odd parity generator. We'll take one of them as an example. And I should be able to understand the other one. So the first one is it's an even parity generator. Okay. So which means is if you are sending a 3-bit binary number to the receiver, okay. So for example, 000 is the data, right? And you want to send another, just one extra bit right after that as a parity bit. So that bit need to be generated because the system doesn't know which kind of bit you want to send, right? If you're defining that as the even parity generator, then the number of ones in the entire data package has to be even. You know what I mean? So for example, A, B, C are all zeros, and you should generate a 0 to make an even number of ones because you want a 0 number of ones in there. And if you got a 1, just one in the data, then you want to generate a 1 as an extra bit, as a parity bit, to have 2 ones in the entire data package to be sent.
That's what you add to make it even.
Yeah, you're adding a 1 to make an even number of ones in the entire data package. So because you are letting the receiver know you are having an even parity generator, so it's going to be an even parity checker as well at the receiver side. So if, for example, if you are sending an even number of ones, right, and one of the bits is going to be flipped, you are getting an odd number of ones, which means it's getting disturbed or there's some disturbance to the system or noises to the system, you're having errors, and you don't want to use that data at the receiver side. So you're asking like, what about 2 bits are getting flipped at the same time? So you're also getting an even number of ones, right? Then your system cannot find out that error. So it's not a perfect error checking system.
How does it work as an error checker?
Yeah, because the receiver and transmitter both know that you are doing an even parity generator, even parity system over here, right? So you are sending even number of ones. And that's agreement in between the receiver and.
So it just checks if the number of ones that are received are even?
Yeah, at the receiver side.
Oh, okay.
So if you have 2 bits getting flipped at the same time, then you won't be able to check it, right? So it's not perfect, but it's still being used in a lot of places. Okay. And if you think about the logic, it's fairly simple. It's just compositional logic. You can put all the inputs and outputs in the truth table. because you know what the inputs are and what kind of outputs do you need for that input as a parity generator, right? So the parity generator is generating a parity bit. So you have 0, 0, 0, you just need a 0. You have 0, 0, 1, you need a 1. So on and so forth. You can easily fill up the truth table. And from the truth table, you can convert it into a logic function. Right, that's a schematic of it. And here's a Verilog code. So eventually, it's simply just AX or BX or C for the even parity generator, for the parity generator. Okay, that's the P. P is a parity bit. It's extra logic in between the three inputs. That's where you'll find out from the logic expression over here, okay, after I simplified it. And then you need a checker as well. So how would you want to design the checker before you look into that? Think about it. So you had a 3 bits as a data, and you are adding 1 bit as a parity bit. So combined, you are sending how many bits to the receiver? 4. Okay. So the checker is going to receive 4 bits. Okay. So it's going to check these 4 bits and have 1 result as well. So eventually, it's just the 4 inputs and 1 output. So that 1 output will be the like error flag. So these are the 4 bits as an input. And if nothing is wrong, usually you give a 0. If something is wrong, you give a 1. Okay? Is this an even or odd parity checker? Even. Why? No. This is the checker, not a.
Oh, the checker.
Yeah, the ones are odd. You're getting a 1 here, right? Is it? Is this odd here? The 4 bits. You got only 1 here, so you need to turn it on. This is the error bit. So you are turning it on. So if you think about that, you implement it on the IPGA board. You got one of the LEDs being used as a signaling LED. Okay, so if whenever you have odd number of 1s being received, you just turn it on. Okay, clear? You don't have to go through this one. You know why we usually don't do the like four inputs, truth tables, and key maps. It's just unnecessary. I never spend that much time in my logic class to, simplify a very complicated logic expression. You never use it in real world. It just use Verilog and like Vivato to synthesize your logic, right? You never do it manually. And also you can do a parity generator and checker as well. Logic expression, checker. Okay, so there are 2 more examples will be included into the tasks of this tutorial. So one is improving the home alarm system. And another one is improving the car parking spot counting system. I will break for 5 minutes and we'll come back and talk about that. And also the specific tasks over here, and also something you need to know in the lab, right? Because you got to understand how to use a 7-segment display on the IPGA board in order to do this. Let's break a little bit, 5 minutes, right? Okay, let's to take a look at the 7-segment display schematic first. You can also find out the link on the Lab's website. I just update it. Make sure you refresh the browser and scroll down to the bottom. Not really bottom, but in the middle probably. I'll be able to see this circuit. Okay, so that's how they make the connections on the board. I know it's not really clear, but hopefully you can see all the letters over here. And if you zoom in, you'll be able to see this little BJT. How many will have been in analog? You analog 1, 2. Okay. So the BJT transistor is a PNP. Okay. If you haven't been in the analog, you don't have to understand what's going on here. But the basic line is you need to know that you need a 0 and 0 to the bottom and the middle to turn it up, to run current through it. See the little arrow here is pointing inside, it's on the top. It indicates it's a PNP transistor. Did you learn PNP?
Yeah.
Okay, so the PNP, the power is on the top, is 3.3 volts. It's trying to run current from top to bottom. Okay, and you can see these are the 7-segment display modules. How many of you have used the 7-segment display in the past? 1, 2, okay. It should be covered in my controller later in the semester.
Why do you use a BJT instead of a MOSFET there?
Cheap and running a higher current. And either one works. I don't think that matters. Yeah, that doesn't matter at all. So it's you have seen this a lot in a lot of display modules. Okay, 7-segment means you got 1, 2, 3, 4, 5, 6, 7. Okay, 7 LEDs can form a lot of letters and numbers in there. So it's being used as a display module. It has this advantages and disadvantages of using that. First, it's super cheap and simple to use. However, it's consuming a lot of power because every single LED is being turned on. It's running a lot of current into it. So it's not really saving power for a system. You have to run a low power device or sensor. You don't want to use this one for your system. It's going to drain the battery very quickly. So you want to use like LCD or OLED, things like that. Okay. So for each 7-segment display over here, it has 7 LEDs and plus the little decimal point. It's called DP. So the name of this point is DP. So if you look at the display module, it has 7 bars of LEDs or LED bars plus 1 little LED dot. All right. So it's basically 8 LEDs for each display unit. You can see inside it's just a little LED like that. And if you want to turn on this type of LED, just for example this one, which side of the diode that needs a higher voltage potential to run current through it? Here or here?
The left side?
So the LED is, or it's considered as a diode, right? So if you want to run current through the diode. So what LED stands for? Light emitting diode, right? So it's a diode. It's an electrical component you can find in the lab. You have to have a higher voltage on the left and lower potential on the right to run current through it to turn it on. Okay, so the way to remember it is if you see a bar, okay, the bar is being drawn here, so you won't be able to run any current. It's going to block any current in that way, but it's able to run it this way. Okay, it only runs current in one direction, and there will be a threshold voltage, usually like 0.7 volts, like the voltage difference in between these two terminals. If it's lower than 0.7, you are unlikely to turn it on. It has to be more than 0.7 volts to turn it on. Very simple to use. Just have a higher potential on the left-hand side and it has to be larger than 0.7 volts to turn it on. That's it. And a lot of times in your in real world, you have to connect a current limiting resistor. So you don't want to directly add a battery. For example, here's a battery. Plus, minus, okay? You don't want to directly add a battery to the two terminals of the diode because you are possibly going to blow it off or reduce the lifespan of the diode. So you want to add a little current limiting resistor because the internal resistance of this diode is really low. If you have a like 1.5 volts battery, for example, and the internal resistance, for example, is 10 ohms. So you are getting like 150 milliamps. It's a pretty large current for that little LED. So you want to limit the current using a resistor in the range from probably 300 ohms to, I don't know, usually 500 ohms. But if you put a 1K there, it's going to dip that LED, but still going to work. Okay? Very basic circuit building stuff over here. One question here. Why do we need a resistor for the LED? What's the name of the resistor? Current limiting resistor. Okay, so we are trying to limit the current running through the LED. Okay. Now let's go back to this one. Do we have a resistor to protect the LED? Take a look. Do we? Yes, we do here. Right? It doesn't have a resistor inside, but it can connect a resistor outside. Okay? And this resistor is trying to limit the current going into the base of the PNP transistor. We don't have to dig too deep into this analog class, but just let you guys know the PNP, so it's the NP here is another diode inside the transistor. So also need a resistor to protect the little pin junction inside it. It's okay. We just need to know that we need a resistor to protect the base. We need a resistor to protect the LED here as well. So this is a transistor being used as a switch. So when you turn on here and here, you will be able to run current from top to bottom. That's the only thing we need to know for this class. Okay. So we need, for example, if you want to run current through this path. Okay. Take a look at it from here to here. Okay. We need W4 and W7 to be 0 at the same time. That's the only thing you need to know for this class. Is that clear? You need a W4 and a W7 to be 0 at the same time to turn on this path. Okay, now let's look at the second one. If you want a current that can run in this path, that's the same transistor, do we need a V4 to be low or high? 0, 1. 0. What about W6?
Could it be U8?
No, just run current through here. That's a V4, right? V4 need to be 0 and the W6 need to be 0 as well. We don't care about the circuit inside right now, okay? But we need all zeros in order to turn on anything, okay? So A means, you see A here, CA, CB until CP, CG, CP. So these indicate that it's turning on, off, it's controlling one of the LEDs in one of them. It's a little bit confusing because I have 4 units. It's actually all the 4 units are being shorted together. So all the A's are being shorted together, and all the B's are being shorted. It's trying to multiplex all the digital pins. Don't think about it's 4 units, but what about just 1? Okay, if you just have 1 display unit, okay, and these are the pins CA, CB, CC until CP. These are these pins. these little dots are being shorted to these connections. Could you imagine that? So here, right, here, 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 here. So these are this side is a cathode. This is anode. Okay? So these dots are the cathode or anode of the individual LEDs. These dots. Are they anode or cathode of the LEDs? Cathode, that's right. Okay. So do you need these dots to be low or high in order to turn on the LED? Low. Great. Okay. So do you need these pins to be low or high to turn on the LED? Low. That's right. So now here's a question. I have 4 units. Each unit takes 8 pins. So for 4 units, how many pins do we need? 4 times 8. 32. Do we have 32 pins? Do you want to use 32 pins on my controller? It's occupying a lot of pin resource on the my controller or IPGA. You want to reuse it? No, you want to reuse it. So if you look at the unit, that's all the wires you have on the unit. It's like 4. If you look at our IPGA, you have your IPGA here, you open it up, you can see that 4 display units are being put together. That's just one module. It's just one module, one block. And they're reusing the data lines on the module. You don't have 32 pins. It's just from A to P, it's the A pins being reused for all the LEDs. So which means if I have an A here, for example, I'm looking at A, let's say E, okay? So let's look at E. So this E here, all right, even though I don't have a circuit drawn on that. So E is this LED on the bottom left corner here, all right? Is this node being shorted to all the E's or just the one E? Just one of the LED, the E LED in one of the unit. What's really happening for the internal circuit? You know what I'm saying? You only have 8 pins, right? So you don't have 8 pins here. But you have like 32 LEDs. All right? You have 32 LEDs, but only 8 pins. Don't look at these pins for now. I'm going to talk about that later. But I only have 8 pins, but you have 32. Let's just look at E. You only have 1 E, but you have 4 E LEDs, right? This is E, right? This is LED E. Okay? You have 4 of them. 1, 2, 3, 4. But I have 1 E here. Only 1 pin for E here. What's happening inside? So if you draw on the paper, so that's E, right? Got 4 E's. So the 4 E's are 4 LEDs. Okay? I'm just looking at E. That's that's E, right? That's a 1 display module, and that's a E. That's another E. For the second one, you got 4 of them. All right, you got 4 E's, but there's only 1 CE pin in the module. That's a module here. Only 1 CE. Okay, only 1 CE here. What's happening inside? Yeah, they're being shorted. How they are being shorted? How could you make it happen? Shorted where? Here? Anode or cathode? Cathode. So what's the consequence of it? If you turn on that LED, all the LED will be on. All the E's will be on at the same time. But you have 4 modules. How do you want to display different things on it? What's going to happen? Or how would you like to, how could you program it or manipulate it to show different digits or numbers on the four display units. Because whenever this is on, all the E's are on. It's the same for the other LEDs, right? If you turn it on, all of them are on. It's going to show the same number.
Is this the thing where it like switches really fast?
Yeah.
I don't really remember how it works.
So it's tricking your eyes, right?
Yeah.
So that's why you have AN on the top. So AN is a pin that is providing another switch on the top. You see ANs. So ANs are the W4, V4, U4, and U2s. So these, yeah, disables, enables, you can do it really fast. So what's happening is, if you, for example, you disable all the three over here and you enable this one only, and you throw a pattern here to the LEDs to display a certain number or letter, and you only enable this one, so it's going to display, for example, 0 here, okay? All right, and then you disable this guy and enable this guy really quickly, and then you throw another number here, so it's going to display a different number over here, and then you enable this one and disable all the three of them and throw a different combination of binary bits for the input. So display, it's going to display a different number. So if you switch it really fast, your eye cannot resolve it, so it's going to looks like a very static number, 4 digits. But actually, it's switching really quickly. If you have a high-speed camera, it's going to detect that, but your eye cannot resolve it. So it looks static. So that's a common way to program microcontroller, one of the microcontroller display modules. And we are going to do that using FPGA's clock in the lab this and next week. Okay. Okay, so continue talking about this this afternoon. It's getting more fun right now. Display and connect to sensors. I'll see you there this afternoon. Okay, be there on time.